let's actually take a look at the code and see what's really going on when we are implementing this Newton-Raphson on the Cauchy distribution. Okay, so over here, I'm going to have, I have the setup of the MLE of the location Cauchy. First thing what I'm going to do, as I've done before, is I am going to set my seed. So my seed is 1, and this I'm particularly ensuring here because I want to ensure that you and I get the same exact data. Again, we have the luxury of simulating our own data in this situation, and we will utilize that luxury. So I set dot seed 1, mu dot star. So the true value of mu is 5, n is 4. So I'm only generating 4 data points from a Cauchy, which I do using a t distribution with 1 degrees of freedom. And I add the mu value over here because I'm just displacing it a little bit by that mu, right? So this is a location Cauchy. Now, I also have a function that calculates the log likelihood. Okay. And so the log likelihood takes a value mu, because remember the log likelihood is a function of mu. I have the values of mu on the x-axis and the log likelihood value for those corresponding values of mu on the y-axis, given the data that I've observed. Now the data that I've observed is in x, and so based on the notes that we just saw on what the log likelihood expression looks like, this is our log likelihood function. Now what I do is I create a grid of values going from -10 to 40 for mu, and then I apply the log likelihood function for all of these values of mu and then plot it. I'm going to take a second. There we go. So now this is exactly what we saw in the notes a few minutes ago. And so I have log likelihood on the y-axis and mu on the x-axis. Okay. Now I'm going to implement Newton-Raphson. And the way I'm going to do this is first I set a tolerance, and I set the tolerance to be 10 to the power -5. And then I create two functions. The first function is f prime, which returns the derivative of a log likelihood for a given data evaluated at a certain mu. Double prime, which is the second derivative for the given data evaluated at a certain value mu. This is basically all the actual f prime and f double prime that we calculated. So I'm just going to run that. And now what I'm going to do is I am going to run the following loop until I actually get convergence. So convergence is going to happen when f prime mu k absolute value is less than tolerance. The current value, the starting value, the current value is now the starting value. I'm going to choose a good starting value right now. So these were the blue dots in the beginning, and that is the median of x. So let's look at what the median of x is. For the data that I have generated, which is x, the median value is 4.6. Now notice that if I had taken the mean, it would be 7.5, which is going to be, somewhere here, which is very far away from the actual optima. But the median, which is 4.59, is actually very close to here. Right? So the mean is a very unstable value for the guess of the location in this case. So that's my starting value. My diff, which is going to be an initial large value that I choose, that will be compared to epsilon. So this is just a dummy value that I give it right now. And the number of iterations, which is basically my count, is 0. I start from mu k to be current value. So it's the current value that I have. Now, as long as diff is greater than tolerance, so as long as the value that I have is larger than my epsilon, and the iterations are less than 100. Now, I'm going to add this because for this example, I'm not sure whether we are going to converge or not. So if I diverge, it will just keep going and going and going and going, and it'll keep generating mu k's, and I wouldn't know when to stop. So I basically put in a filter to say, if it reaches 100 steps, I don't want to go beyond the 100 steps. And the way it updates this is by the following. It updates iteration, so just adds k to k plus 1. The updated value is the current value minus the first derivative divided by the second derivative. I update the sequence of mu k. So I just make sure I combine all the updated values that I get. And I just see what the difference is, as in what the gradient of f at this particular current value is. And then I set the current value to be the updated value so I can keep repeating this process, right? So this is my Newton-Raphson method. And when I do this and I put the current value, I get that the current value is 4.56. And actually my whole mu k sequence is 4.59, which is where I started from, to 4.5619 to 4.5620 to 4.5620. And at that point, I've converged. So in only 4 steps, it actually converges to the actual optima in this case, which we can see whether it's the global optima or not. So what I do is in evals, I calculate the log likelihood value at each of those values of mu, and then I plot my log likelihood function, which I already have, and then I plot the value of theta, which over here is all the values of theta. So all 4 values are plotted, but they're so close to each other that you can't really see the difference. Now I'm going to start from a bad starting value, which is 7. So I'm going to start from a starting value here and repeat the exact same process, right? So the only difference is okay, I'm going to repeat the exact same process. I'm going to start from 7 and run this loop, okay? And this is exactly what I see. So if I print mu.k, which is my whole sequence of mu's, I see a start at 7, then go to 9.98, then go to 13.33, and then keep going closer and closer to 13, which is the place of local minimum, which is not where I want to go. Right? Again, exactly what we saw in the notes. And now I start from the worst value, which is 19. Right? And I start from there and I continue the same process again. And I see that that's exactly what happens. If I look at mu k, you know, in like 19, 20 steps, I've gone so far away that it doesn't want to go anymore. I start from 1.9, right? Or 19, sorry, then go to 23 or 24, then go to 35, then 60, then 112, right? Then 200, and then 400, and then I diverge eventually to about 1 million. So I'm really diverging, I'm really going away. Okay, and I can see that over here. You can imagine it'll just keep going in this direction. Okay, so in the blue I have the good starting values, in the red I have bad starting values, and in the green I have horrible starting values. Now I can do this again with a different seed. Now why am I changing the seed? Is because remember I generated random data. Right? Now, like I said, the shape of the log likelihood will change based on the data generated. So here I generate again 4 data points, but completely different data because my seed is different. For the same value of mu, by the way, mu is still 5. And now I see that for this seed, my likelihood, because my data observed has changed, my likelihood function's shape has changed, and actually where the maximas, etc., occur has also changed. So we see a little bit of dip here, and we have something that looks like this. Now when I start from median, which is a good value, and I see what the iterations look like, I see that actually median is here, and as it turns out, median happens at a local minima. Okay, so I'm very close to the optimizer, but actually there is a minima exactly where the median is. And so when I start from the good value, I actually don't really converge to the optima. When I start at x equals 2, which is somewhere here, okay, I can repeat this again and I get something like this. Now x equals 2 over here, I converge over here. When I say converge, if I look at the actual points, I start from 2, I move to 2.038 to 2.039 to 2.039, something very, very close. And that actually looks like at least it's a maxima. I don't know if this is a larger one or this is a larger. And when I start at, 19, I get something like this. Again, it just diverges. Now we can start also at a value that's somewhere, let's say here, and see what happens. So I can start at that looks like it's maybe 8. And if I start at 8, it's still diverging. So 8 is not really where this is. So maybe it's like 6. So I just want to see what happens if I start very close to here. Right? Do I actually get these green dots to go closer to the maxima? And actually I do, right? So when I start here, I notice I sort of flip around and I go converge to the optima here. So if I look at what mu k looks like, I'm at 6, then I go to 4.5, then I come back to 5.5, then I go to 4.55, then 5, then 4, and then in this way I'm sort of converging to 4.93 roughly is where the maxima occurs. And this 4.93 is actually closer to my actual truth because my true mu is 5. But you can see the objective function is now very difficult to maneuver because this red one could also be a maxima, this green one could also be a maxima. Okay? Point being that if your objective function is really tricky, and if your objective function is non-convex, then Newton-Raphson is not going to guarantee convergence to you. Even if you choose really well-chosen starting values, you might end up in a situation that's something like this, where there's very little movement or freedom for you. Okay, so Newton-Raphson is advisable to be used predominantly when you have a concave objective function.